As we continue our treatment on waves, I'd like to take a brief detour and talk about light. So I'm going to take a very quasi-historical approach here and point out that early on, when people were thinking about the nature of light, there was a debate as to whether we could think of light as as some sort of a particle or as some sort of a wave. So, for instance, Newton was a big proponent of the particle view. And here he's saying that light was some sort of small particle. And today we actually give that name, the particle, a name. We call it a photon. So you can see that Newton wasn't completely wrong. Arguments in his favor, for instance, were things like looking at how light reflects off a mirror. Light reflects off a mirror in exactly the same way that a billiard ball would bounce off the rail of a perfect pool table or something like that, which certainly lent a lot of credence to the particle view, and there were other bits of evidence that backed that up. What made things a little tougher for him was describing refraction, which is how light bends, say, when it goes from air to glass or something like that. But even there, he could make the particle view work. It just seemed kind of strained. Now, the other workers, notably Christian Huygens, proposed instead that that light was some sort of a wave. And the evidence for that wound up coming from an experiment done much later by Young, as in Young's modulus, same person, where he was able to show that light could be made to interfere in the same sort of way that water waves did. And this turned out to be very hard to resolve by the particle view, and pretty much people gave up on it, on the particle view at that point. However, it turns out that it's more nuanced than that. So to explain the more particle-like things, Huygens came up with what was called the ray approximation. Which showed that if you had a plane wave coming in, you could erect a geometric ray perpendicular to that plane wave, and you could get the rays that were associated with the waves to reflect off of a surface the same way that a particle would. So that recovered most of the particle-like things. And then Young and others saw things that were much, much, much harder to explain away by the particle model. So this is sort of the historic debate. And with time, eventually, by the time we got to the 19th century, pretty much the consensus had settled in that light was some sort of a wave. However, the workers at the time only understood, the only kind of waves they knew about were mechanical waves, which it turns out light is not. And since they only knew about mechanical waves, they proposed that it would be waving in something that was permeating all of space, which they gave the name the luminiferous ether. Now, this is a model that has since been discarded. In particular, there were issues that once the Maxwell equations, which described the nature of light, came around, one of the big issues with this model is that the Maxwell equations predicted that everybody should measure the same speed of light. And by that I mean, imagine, say, that I turn a laser on and you measure the speed of the light coming out the laser port. You would get just a shade under 3 times 10 to the 8 meters per second. Now, if we imagine me taking that laser and I go flying off in some rocket ship at, let's say, 2/3 of the speed of light, 2 times 10 to the 8 meters per second, and I shine that laser beam out the window, I would still be measuring the speed of the light of that laser beam as 3 times 10 to the 8 meters per second. And this is the weird bit, so would you. Now, if it makes you feel any better, we would disagree about the color of the light that comes out of the laser. But both of us, even though I'm carrying the laser at 2/3 the speed of light, both of us would agree that the speed of the light coming out of the laser was just a shade under 3 times 10 to the 8 meters per second. And this is what the Maxwell equations predict. And experiments by the team of Michelson and Morley, physicists from Ohio, were able to demonstrate that, yeah, this is indeed exactly what happens, that different observers moving with respect to each other, measuring the speed of light coming from the same source, will both agree that that light is going at the same speed, 3 times 10 to the 8 meters per second. And this turns out that this luminiferous ether model just could not work for that. So that was the first problem. So it led to discarding that. But yet, light still had these wave-like properties. So what was going on? Add to that, in the era of modernity for physics, so in the modern physics, which basically starts in the early 20th century, there were two problems that were found with the wave model of light. One was the photoelectric effect. Details about that did not match what the wave model was predicting, electric effect. This is actually the phenomenon by which solar cells work. You shine light on certain kinds of material and you can drive an electric current. Although the wave model of light predicted that there should be a photoelectric effect, pretty much any calculation you did said that it should take, for a realistic light source shined on a realistic piece of material, it should take about a 2-week delay between when you turned on the light and when you first started seeing an electric current. That's not how solar cells work. It's pretty much instant. And at first it was thought, okay, this is just problems with maybe making too many approximations or something like that. These sorts of things have crept up before. Nobody got all that worried about it. But people spent like the next 20 years working on it, doing more and more careful calculations, only to keep getting basically the same answer. So that was one of the big problems that we had. Now there was one other problem that showed up as well, and that was the issues regarding the spectrum for black body radiation. So in thermodynamics, we saw that there are 3 modes by which heat can be transferred: conduction, convection, and radiation. So conduction is the most efficient form of heat transfer. That's just when two things are pretty much in direct contact. Convection is via a fluid, so say the air in the oven or something like that. And then finally, radiation. It turns out that all objects that have a temperature emit light. This is called black body radiation. And it turned out that the details of the spectrum did not match up. Specifically, there was a problem called the ultraviolet catastrophe. The calculation based purely on the wave model of light predicted that, and classical physics, both of those together, predicted that as wavelengths got shorter and shorter and shorter, the intensity of the light emitted would just head up to infinity with decreasing wavelength. Well, there's a problem with that. That means that literally everything would be radiating an infinite amount of power. And so this makes no sense. What you do see is for long wavelengths, everything matched up with the classic calculation just fine. But short wavelengths, instead of heading up, it curves back down and heads down towards zero, which is a good thing. It turns out that we had to have a complete rethink of all of physics in order to resolve both of these things. So the resolution to these two problems is that everything has both a wave and a particle nature. This is true for matter, and it is also true for light. So in the modern interpretation, what we say is that the wave nature of light, or the wave property of light, determines the probability probability of detecting a photon. So it's not either or. Particle versus wave. It's both and. So everything, light included, has both a wave and a particle nature, and the wave property dictates the probability of detecting the particle should you go looking for it at a particular location. This is at 100% at the core of modern physics. Now, I'm going to defer treatment of wave-particle duality and instead just go back to talking about our best understanding of the wave model of light, understanding that there is this connection that the intensity of the light wave is dictating the probability of detecting photons. So in this animation right here, what you are looking at is our model of an electromagnetic wave. So what you are seeing here is at these points in space, a property of that point of space called the electric field in the case of the red and the magnetic field in the case of the blue are varying. Not only do they have a magnitude, but they also have a direction. And these are properties of the points in space that you see the tails of the vectors at. So there's nothing actually being disturbed up and down. Now, it turns out that in a study of electricity and magnetism, what you'll see is that the Maxwell equations predict that a If you have a electric field that varies with time, that creates a magnetic field at right angles to it. So the red is the electric, the blue is the magnetic. And vice versa, that a magnetic field that varies with time creates an electric field. So these continuously changing fields actually keep continuously creating each other. Now you'll see that light is a transverse wave in the sense that the waving is happening in the direction perpendicular to the propagation. The difference is that nothing is being disturbed out of place. No medium is being disturbed. We're just seeing electric field vectors and magnetic field vectors that are continuously changing in directions perpendicular to the propagation of the light wave. Now, if you're in a vacuum, the light always travels at just a shade under 3 times 10 to the 8 meters per second, and we give that the special symbol c. So the speed of a wave is noted with of light is noted with a c for speed of light in a vacuum. If you are in any kind of medium other than a vacuum, light will propagate more slowly through it because of how the electric field in particular interacts with the material that makes up the medium. However, in the case of air, it's only a very, very small reduction in speed. However, in materials like glass, it can be pretty substantial. Light can be traveling at 3/4 or even 2/3 of the speed of light in a vacuum in a material like water or glass, for instance. Now, just a couple of other things to point out as long as we're here. And again, I'm not going to get into it in any big detail here because I feel it's best left for a treatment in an electricity and magnetism course. But the way that you pretty much make any light wave is you take a pile of charge, usually electrons, and you shake them up and down. So what will be happening is we can be shaking some electric charges up and down. This will induce both electric and magnetic fields. How that happens is beyond the scope of this treatment, but that happens. And then that eventually sets up the self-reinforcing chain between electric and time-varying electric and magnetic fields that I was mentioning a little earlier. The other thing, too, is that roughly, in order to both make and detect any kind of electromagnetic wave, and light is an example of an electromagnetic wave, the thing that made it and the thing that detects it have to be within about a factor of 1,000 or so in size of the light wave actually being produced or detected. All right. So just to give some quick example of that, you can find, again, since I want to avoid any sort of copyright strikes, a quick Google search will find all sorts of diagrams of the electromagnetic spectrum, but I just thought I would talk about, in terms of wavelengths, roughly what makes it and what can detect it. So if you're on the order of about 10 to the negative 12 meters or so, that seems like something really small. This is firmly in the land of what we call gamma rays. And you'll see these sorts of things happen in nuclear nuclear reactions. Now, a typical nucleus is somewhere in the ballpark of 10 to the negative 15 to 10 to the negative 14 meters or so. So this is within our usual guideline of a factor of 1,000 or so. So going ahead a little longer wavelength in the about 10 to the negative 10 meter range. That's where you'll have X-rays. Pardon me here, there's not supposed to be a hyphen there. And you'll find this in certain kinds of atomic transitions. And an atom is typically on the order of 10 to the negative 10 meters across. Light, visible light, will be more on the order of about 10 to the negative 7 meters or so. Yeah. Hundreds of nanometers. And again, that's within the ballpark for atoms, so atomic transitions are, again, certainly a way that we can make those. And then you can get to bigger things. For instance, infrared is in the about 10 to the negative 5 to 10 to the negative 4 meter kind of range. And that's about the same kind of size as a cell or bacterium. So if you think about, you see infrared images of people walking, that's from the light being emitted from the cells that are undergoing cell respiration in the body of the person. And then microwaves are roughly in the 10 to the negative 3 to 10 to the negative 2 meter kind of range. And a cell phone is a perfect example of that. What dictates the overall dimension of a cell phone is the battery. Turns out that your cell phone is almost entirely battery in order to provide long enough life. But the reason, for instance, that it isn't any skinnier than it is that turns out to be a pretty good size for the antenna that detects the microwaves. The microwaves that your cell phone uses are in the millimeter to centimeter kind of range, and the antenna that you're using to detect it is a few centimeters. And then finally we can get out even longer. So in the anywhere from 10 to the negative 2 meters to 10 to the plus 3 meters and up, that's radio, and certainly a radio antenna will both detect and receive those. So for instance, in order for radio waves to make their way through ocean waters, when governments are trying to communicate with submarines, submarines will carry a long cable, several kilometers long, that they reel out with the whole point of trying to receive a very long wavelength radio transmission. And there are radio transmitting facilities that have antennas that are, tens of kilometers long, transmitting these signals. And then you have these very long cables being hauled behind, reeled out by submarines to detect the signal. Now, usually you transmit just a few characters that a code book will then say, now go and surface your sub at these exact coordinates to receive a satellite transmission at a specific place and time. But that is an example of a very long wavelength radio wave that would be in the kilometers kind of range. So just to give some sense, we could take a look at, say, FM radio. The radio station CIMX has a frequency of 88.7 megahertz. So we could try to figure out what is the wavelength. Now, just like any wave, it will be true that the speed of the wave equals the frequency times the wavelength. Now here we're using c because our wave is a light wave. So the wavelength will be the speed of light over the frequency. So call it 3 times 10 to the 8 meters per second. Close enough. 88.7 times 10 to the 6 hertz. Hertz is 1 over seconds. I'll cancel the 1 over seconds there, leaving me with meters. And I get 3.38 meters. So the wavelength of a typical FM radio transmission is on the order of a few meters. And that dictates in part the dimensions of the slot in which you stick a radio receiver in a car. You take a look at a typical DIN slot that a radio receiver goes into in a car. That's tens of centimeters wide. So again, trying to be within this case about a factor of 10 or so the length of the wave. So the antenna itself is actually just hidden in the box. Part of the reason why vehicle manufacturers are going away from offering AM radio, or if they do, it's really crappy, is because they don't, in order to not ruin aerodynamics and in order to reduce problems with vandalism, they've gotten rid of having antennas that were just plain attached to the front of the car. Because AM radio operates in the kilohertz region, the wavelengths are much longer, in hundreds of kilohertz. So the wavelengths are about 100 times longer. So you're talking wavelengths that are a few hundred meters. And so in order to be able to receive them at all, you pretty much need an antenna that was at least, on the order of about a meter or so. And so older cars would have an antenna like that attached to the front. Well, that's not good for aerodynamics, and it certainly was a big target for vandals who would just come along and snap off the antennas just for the giggles. So this has led to either just making do with a smaller antenna that doesn't receive as well, so you get crappy FM, but you can at least keep it inside the car, or you just give up on offering AM radio altogether, which a lot of vehicle manufacturers are starting to do. All right. One other thing that's sort of unique about light, otherwise light follows the inverse square law and all of that same kind of stuff. But one thing that is unique about light is how we usually characterize the speed. Instead of just giving the speed, we usually quote a number called the index of refraction. So the index of refraction for any medium is defined, so the triple equal sign means by definition, the speed of light in a vacuum over the speed of light in the material. So it turns out that when you go on to do optics, Snell's indices of refraction are much more convenient to work with than actual wave speeds. So that's part of where that's coming from. But just to quote one useful example, we remember that if a wave goes from one medium to another and it changes speed as a result, we saw that the frequency stays the same, but the wavelength will change. So following that thought, let's say that I have a wave of light in a vacuum, or you could imagine air, they're close enough in speed. And then let's say glass or something like that over here. So here the index of refraction is basically 1. Here it's on the order of 1.5. We can think about what happens to the wavelength. So here's the wavelength in a vacuum. And because the light goes slower in the glass, we know that the wavelength will be in the medium will be shorter. But by what percentage? Well, we can realize that by v equals f lambda, we already saw that the wavelength is equal to v over f. Now, using this definition here, I can rearrange this to get that v is equal to c over n. Like that. And I can rearrange it further to say that the frequency then will be c over n. Whoops. Sorry. Let's try that again. No, that's correct. So c over n f equals lambda, or f equals c over n lambda. All right, so now we can do this for two different materials. So say one of the materials, so if one of the materials is a vacuum and is just plain 1, but since the frequency has to be the same, that'll also be true. So say lambda vacuum. This will also be true in some material, in some medium. So lambda medium, like that. All right, we can cancel the c's. Be left with 1 overs. And if we rearrange, we get that the wavelength in the medium will be equal to the wavelength in the vacuum over the index of refraction. So that's really handy. So say if the index of refraction is 1.5, then we know that the wavelength in the medium is 2/3 that in the vacuum. Alrighty, so that takes care of as much as I want to introduce about the wave nature of light. So I'll catch you in the next video.